In this lecture, we will continue our study of inductive proofs. Today I will introduce a variant of the principle of mathematical induction. In fact, two variants we will see today. So the first one is this is again a weak form, but I would say generalized weak form. Okay, so this goes like this. So I choose two constant positive integers, or maybe in general I can choose constant integers. One is n0, this may be in n0, it may be 0 itself, and the second one is a positive thing, k. This is in n or z plus. And suppose again that Sn is a statement about an integer n greater than or equal to n0, and suppose that we have two things, Sn0 is given to be true, but this is not the only thing. Sn0 plus 1 is also given to be true. Sn0 plus 2 is also given to be true, and so on until Sn0 plus k minus 1 are true. Second, for all n in, or I will better do this thing. For all n greater than or equal to n0, if Sn plus 1, Sn plus 2, and so on, up to Sn plus k minus 1 are true, then Sn plus k is also true. If these two conditions hold, then we have Sn is true, for all n greater than or equal to n0. So this is generalized because in the last class we have considered only the special case k equal to 1. Now we allow k to be 2, 1, 2, 3, 4, 5, but some constant thing. And we will also study a format which is slightly stronger assumption than this weak form. Okay, so instead of assuming just only one thing, I am assuming k things at the beginning, and whenever the consecutive k things are true, then the k plus first one is also true. Okay. So this is again a weak form, but but this is just a generalization because I am introducing this k. Earlier it was only 1. Okay. I will not again prove the same thing. Proof, I leave it as an exercise. You may, for example, use UL ordering principle. So I leave that thing to you. Let us assume and see some applications of this generalized induction. Okay. Okay, so I start with example 1. So recall how we have defined Fibonacci numbers. F0 is 0, F1 is 1. Subsequently, Fn is Fn minus 1 plus Fn minus 2. Okay, the sum of the previous two elements in the sequence. Now, today I will start with something called Luca numbers. They have some relation with Fibonacci numbers. So Ln, they are defined as follows. L0 is defined to be 2. L1 is defined to be 1. Subsequently, it is the same thing like Fibonacci numbers. Ln is Ln minus 1 plus Ln minus 2 for all n greater than or equal to 2. So what I will now prove by our new form of induction is that Ln equal to Fn minus 1 plus Fn plus 1. Of course, this does not make sense for n equal to 0, but for n equal to 0, f minus 1 is not defined. So I prove it for all n greater than or equal to 1. Okay. So proof. Okay, so in this case I will have k equal to 2. So in the basis case I will have to prove for n equal to 1 and n equal to 2. So there are two basis cases. N equal to 1. Then what does it say? L1. L1 is, did I make a mistake? No, I think it's okay. L1 equal to 1. And Fn minus 1 plus Fn plus 1 is, n minus 1 is F0, n plus 1 is F2, which is 0 plus 1 equal to 1. So 1 equal to 1. No problem. But this alone will not suffice. Because k is 2, I have to prove another thing, n equal to 2. So what is L2? L2 is by this construction, L1 plus L0 or L0 plus L1, which is 2 plus 1, 3. On the other hand, the right hand side is F1 plus F3. F1 is nothing but 1, 1, 1, then 3, 2. 1 and 1 is 2, F3 is 2, so this is 3. Right. Okay, so since k is 2, the basis involves two initial conditions. Only one will not do. And the inductive step, we will take sum n greater than or equal to 1, and I will make two inductive assumptions. Okay, assume that this holds for n and n plus 1. Okay, the assumption, assume that Ln is Fn minus 1 plus Fn plus 1, and this is also true that Ln plus 1 is Fn plus Fn plus 2. And then I have to prove the same thing for Ln plus 2. Right. Then what is Ln plus 2? From this definition, this is Ln plus 1. Therefore, now I can use this equalities. Ln is equal to this, Ln plus 1 is equal to this, and I reorganize these things like this: Fn minus 1 plus Fn plus Fn plus 1 plus Fn plus 2. Again, by definition of Fibonacci numbers, this is nothing but Fn plus 1 and this is Fn plus 3. So I can formally write it as Fn plus 2 minus 1 plus Fn plus 2 plus 1. Okay, so the basic difference is that I have to consider two basis cases. However, here also I make inductive assumptions for two consecutive values of n. Okay, this is how this is different from the previous, I would say, weak form. Okay. Fine, so we proceed to another example. This is again a very interesting example. Open a new page. Okay. Okay, so I will come to the general result little later, although I will not prove it, but let us work out an example. Suppose that we have 4 rupee and 7 rupee coins. Okay. So, and you want to, you are given an input n in z plus, and your question is to find out whether you can, suppose you have an unlimited supply of 4 rupee coins and 7 rupee coins. So your question is, the question you face is that whether n, this integer amount n, can be exchanged by 4 rupee coins and 7 rupee coins. What I will prove that if n is greater than or equal to 18, then n rupees can be exchanged by coins of the given denominations. Proof. Okay, so traditionally I use another color, maybe green. Okay, here actually I have n0 equal to 18 because the assertion starts from 18. And we will soon see that we will take k equal to 4. That is, I will proceed by induction with n0 equal to 18 and k equal to 4. So the basis involves 4 cases: 18, 19, 20 and 21. Let us see that they can be done. So what is 18? It is 4 plus 7 plus 7. What is 19? 4 plus 4 plus 4 plus 7. What is 20? 4 plus 4 plus 4 plus 4 plus 4. Whereas 21, 7 plus 7 plus 7. Since k equal to 4, I have to consider 4 basis cases. And then induction. So assume that n is greater than or equal to 18, n0, and n plus 1, n plus 2, and n plus 3 rupees can be exchanged using the given denominations. Okay. Then I have to show n plus 4 can also be exchanged. Now this step is quite straightforward. Since n can be exchanged, we just add another 4 rupee coin. Fine. So inductive part is easy. Here I have to show 4 cases. This is important. 4 cases, 4 base cases must be considered, and here 4 previous values. Okay. So most of the time say that I am not using that n plus 1 can be exchanged, n plus 2 can be exchanged, or n plus 3 can be exchanged. But that doesn't matter. Okay, if n can be exchanged, n plus 4 is, we are just not using this n plus 1, n plus 2, n plus 3, but in other proofs we actually use. For example, in the last proof, we actually used all the up to k minus 1. Here I am not just using it. Okay, so this problem is very interesting and has a long history. So which I tell a little bit about this problem. This is named after Frobenius. This is called Frobenius coin problem or Frobenius coin exchange problem or something like that. Okay. So, in general setting, you are given A and B, 2 denominations. So, in our earlier example, A was 4, B was 7. Okay. And then, Frobenius asks the question, what is the largest n that cannot be exchanged by coins of these denominations. First of all, you see that if GCD of A and B is greater than 1, let us call it D, then all the coins, all the sums that can be exchanged will be multiples of D, right? And therefore this question, okay, this is a question. This question makes no sense. There are arbitrary large integers which are not multiples of D that cannot be exchanged by coins of this denomination. So we assume that GCD AB is equal to 1. Then this makes a sense. So in our case GCD of 4 and 7 is 1. And therefore we at least saw in that example that from some point onward we can represent everything. On the other hand, you just figure out, if I given 8 from 18 onward, it is 2 approved, 17 rupees cannot be exchanged. You try it, you will fail. In fact, Sylvester proved that in this case, when GCD is equal to 1, this largest amount that cannot be exchanged is nothing but A minus 1 times B minus 1 minus 1. After this, if I add 1 to it, A minus 1 times B minus 1, everything can be exchanged. So in our case, this was 4 minus 1, 3, 7 minus 1, 6, 18, 18 minus 1, 17 cannot be exchanged, but 18 onward everything can be exchanged. Well, how to prove this? I will not do it because it's not so simple. It's not very difficult either, but it involves some amount of number theory. The fact that anything greater than or equal to A minus 1, B minus 1 can be changed by A rupee and B rupee coins is a little bit easier to prove. Actually, you can use something like extended GCD, but this cannot be represented, maybe very difficult to prove. I think I know a proof, I do not remember it for the moment. Only I would say super interested students may try to prove. In any case, because we have considered a special case of this Frobenius coin problem, I think it is good that we introduce the problem itself. Okay. Again, when you want to prove this, if you are super serious or super inquisitive, maybe we think about other things. Induction will perhaps not help. I am not completely sure. Okay. Anyway, so let us move to another example. Which one shall I take? Okay, this one is okay. Good. So this is my example 3. So like Fibonacci numbers, let me define another sequence. A0 is 0, A1 is 1, and let's say A2 is 2. Subsequently, I define AN minus 1 plus AN minus 2 plus AN minus 3, the sum of the previous 3 terms in the sequence, and this is defined for all n greater than or equal to 3. Then I claim that An is less than 3 power n for all n greater than or equal to 0. Obviously, this is a little bit synthetic exercise, but still, it's not a good and it's not a bad one. Okay, now this holds for all n greater than or equal to 0, so my n0 is 0. And because each term depends on 3 previous terms, our k will be 3. So I will have to consider 3 basis cases. Okay. So for n equal to 0, A0 is 0, which is definitely less than 1, which is 3 power 0. N equal to 1. This is the second basis case. A1 is 1, which is definitely less than 3 or 3 power 1. Final thing is n equal to 2. A2 is 2, which is definitely less than 9, which is 3 square. So the basis holds, but you have to consider 3 cases. Then we have inductive step. So take sum n greater than or equal to 0 and assume, this is the induction assumption, that a n is less than 3 power n, a n plus 1 is less than 3 power n plus 1, and a n plus 2 is less than 3 power n plus 2. Then a n plus 3, which is nothing but the sum of the three previous terms, a n plus 2, a n plus 1 plus a n, this is less than 3 power n plus 2, second one is less than 3 power n plus 1, third one is less than 3 power n, but 3 power something is an increasing function of n, so this is less than 3 power n plus 2, 3 power n plus 2, 3 power n plus 2, which is equal to 3 times 3 power n plus 2, which is equal to 3 power n plus 3. So that completes the inductive proof. Okay. Okay. So, this case is also quite important, and we will use this form of induction many times in future. But for the moment, I will end this session after telling yet another form of induction and giving an example of that form. So once again, this is principle of mathematical induction, but now we are talking about a strong form. Okay, so once again we can start from something like n0, but maybe let's start with n equal to 1 or 0, whatever. Okay, so once again let's say Sn be a statement about nz plus such that the following two conditions hold. S1 is true, and second, let's say maybe for all n greater than or equal to 1, if all of S1, S2, S3 and so on up to Sn are true, then Sn plus 1 is true. Then Sn is true for all n z plus. Again, I am not going to prove it. You can prove it using the principle of well ordering principle. So, why is this called strong form? In the first form that we have seen, the very special weak form, The assumption was if Sn was true, then Sn plus 1 is true. Okay. And in this, I may go here. In this generalized form, I made assumptions about k of these things. But k is still a constant. 2, 3, 4, this kind of examples we have seen. But now I am assuming all of this S1, S2, S3 Sn are true. And then Sn plus 1 is true. So this assumption is very strong. That is why it is also, it is often called the strong form. And proof, again, I leave it as an exercise. But let us see an application of this strong form. We will see other applications in future classes. Okay. Let us now do this example. Okay, so you know what merge sort is. So let me just quickly recollect. So you want to sort an array of n integers, maybe integers, doesn't matter, integers are floating point numbers or something, but sorting makes sense. So if n is small, like 0 or 1, okay, the last page, again, proof is exercise, and another note, we may start, not necessarily from 1, but from any n0, n0. Okay. So in this case, not sort case, I am starting from n equal to 0 instead of from 1. So if n is 0 or 1, then there is nothing to be done. So you just simply return. Because a 0 element array or a 1 element array is already sorted. Otherwise, what you do, you break down the array at the center. Now n is not necessarily even, then if it is n is even, then of course this breaking is very even, n by 2, n by 2. In general, I have a situation like this. One half is slightly bigger than other half. This is the floor, this is the ceiling, and this is the floor. Then we make two recursive calls on this part and this part, and the recursive calls give sorted first half and the sorted second half. So, and then you simply merge using a procedure that I hope you remember. Okay. So recursively sort, two recursive calls on each half, and then this is followed by a merging process. Okay. So I want to investigate what is the running time. So on an array of size n. So since if n is 0 or 1, there is nothing to be done, so we can always assume maybe something like t0 equal to t1 equal to 1. The function is called and simply returned. Yes, sir, this takes just 1 unit of time. Otherwise, we make two recursive calls, one on ceiling n by 2, other on floor n by 2, plus the merging step. And if you recall first step, it's roughly proportional to the total number of elements in the two halves, which is n. So it is some constant timing, so we just for simplicity we take this is n. Okay. Whenever greater than equal to 2. Okay. Okay. Now, when I want to form closed form formulas for this, I will make an assumption that n is always a power of 2, such that I do not have to consider this floor or ceiling functions. That will actually simplify my proof, but in order that that proof makes sufficient sense, this we will cover later, we require this function Tn to be increasing. Okay. So Tn is an increasing, okay, we formally call increasing, but we mean non-decreasing. Of n. So what does it mean? So if you increase n, the value of t of n does never decrease. Equivalently, this says that Tn is less than equal to Tn plus 1 for all n greater than equal to 0. Okay. So, I am going to use this. I will prove it for one thing, and I will assume it for all S1 through Sn, then I will prove it for Sn plus 1. Okay. And this proof will be in two cases. So, I will prove this assertion. The running time on an array of size n is less than equal to Tn plus 1. Of course, sorry, I will not prove it for n equal to 1, I will prove it for n equal to 0 because I now started from n equal to 0. Okay, so let us see the proof. Okay, let me once again switch to another color because it's a proof. Basis. I have assumed that T0 equal to T1 equal to 1. Therefore, it is definitely true that T0 is less than equal to T1. Okay, only one case. For induction, I will assume that T0 is less than equal to T1, less than equal to T2. All these inequalities I will assume. Up to n, right? Yeah, up to n. Tn less than equal to Tn plus 1. Okay. Then, we need to prove right. So I will assume all of this. Of course, I will not use all of this, but some of this I will use. But the thing that I use as we increase n and n, it is further and further away. An assumption I have to use, which is further and further away from n plus 1. Okay. So, there are two things. I will consider two cases. N is even. Okay. And the second case I will assume is that n is odd. Okay. So if n is even, I can write n equal to 2k. But then what is n plus 1? This is 2k plus 1. And if n is, okay, sorry. Okay, fine. N is anyway 2k. And what is n plus 2? This is 2k plus 2. In this case, from the recursion, I have Tn plus 2. This is even. So I have Tk plus 1. Floor and ceiling of this by 2. N plus 2 by 2 are n. Plus Tk plus 1. Plus n plus 2. whereas Tn plus 1 is odd. So I have the floor of 2k plus 1 by 2. Okay, sorry, the ceiling is k plus 1 and the floor is k. And I have n plus 1. Now if I subtract, I see that Tn plus 2 minus Tn plus 1. 1 t of k plus 1, 1 t of k plus 1 cancel. Plus tk plus 1. Now this k will appear somewhere here. Sorry, I made a mistake. Let me correct it. This is tk plus 1 minus tk plus 1. Okay. So now this quantity tk plus 1 is greater than or equal to tk because somewhere in the middle I have tk less than or equal to tk plus 1. Right. So this is greater than or equal to 0 plus 1, which is 1, which is greater than or equal to 0, and therefore I can conclude Tn plus 1 is less than or equal to Tn plus 2. And in this case, it is very similar. If n is already of the form 2k plus 1, then Tn plus 2 minus Tn plus 1 will be, the first one will be 2k plus 3, right? 2k plus 3 means k plus 2, k plus 1 plus n plus 2 minus 2k plus 2, so this is 2k plus 1 plus 2k plus 1, tk plus 1 plus n plus 1. This will simplify, this and this will cancel, this one. I will have tk plus 2 minus tk plus 1 plus 1, and this tk plus 1 is less than or equal to tk plus 2 by strong assumption, somewhere again near the, somewhere near the center. So this is greater than or equal to 0. Okay, so this is greater than or equal to 0. Tk plus 2 minus tk plus 1 is greater than or equal to 0. This is also greater than or equal to 0. So this is greater than or equal to 0. And therefore, Tn plus 2 is greater than or equal to Tn plus 1. Okay. So now, definitely, if I use only the extended or generalized weak form, I cannot proceed. Because there I make an assumption for some constant number of previous cases, k, right? But here, as n grows, the inductive assumption that I use is going further and further away from n plus 1. So no constant can bound it. Okay. Therefore, it's a good idea that I assume that this holds for all 0, 1, 2 up to n. Okay. And then we will see many more applications of such strong assumption, the strong form of inductive induction in later classes. Am I left with anything important for today? I do not think so. So let me stop at this point of time, and I hope I again have spent nearly an hour's time, if not longer. Okay, so bye for the moment.